Today is the first day of talks, and it's a pleasure to me to introduce Gabriela Gutierrez Guillén. She completed her bachelor's and master's degree under supervision of Professor Laura Ortiz, and after that she did his PhD under supervision of Pablo Mardesic and Dominique Soigny in Dijon. And she's doing postdoctoral research at École Normale Supérieure Lyon. And today she's going to talk about, can we detect a physical phenomenon from geometry of a differential equation?
Thank you very much, Jocelyn. Thank you very much for the invitation, Laura. It's a great pleasure to be here. And I have to say also that it's an honor to open this series of talks and also to speak after Professor Ilyashenko. So for the people who don't know me, I will say that I'm the spice called physics in this group, because what I do, it's the geometrical study of ordinary differential equations that comes from physics. And today, I decided to speak about a joint work with Aldo Arroyo from the Sao Paulo University, Pablo Mardesic and Dominique Soigny from the Burgundy University. So the general idea of this talk, I want you to imagine, like in a very abstract way, that you have a physical phenomenon that you want to understand. So this physical phenomenon will be modeled by an ordinary differential equation. And usually, in this ordinary differential equation, you will have some restrictions that come from nature. So you have two options. First, you forget about these restrictions, and you do a study for the dynamical system. But then you remember that you have some restrictions. And the question is, if we can detect if there is a explicit mark of these physical constructs in the geometry of the differential equation. And I want to show you today that for a specific system that describes the rotations of objects that doesn't deform, this is true. So there will be a difference if you consider or if you don't consider the physical restrictions when working with this system. So this is the objective, and in particular, one of the places where we will see this difference, it's in an effect called the tennis racket effect. So what I'm going to do is to describe what is the tennis racket effect. Then I will show you where we can detect this difference when considering or not the physical restrictions. And after, I will take advantage of all the construction to present a previous result that we have, just because I feel that it fits perfectly with this, with the subject of the conference. So let's get started. So what is the tennis racket effect? So we need to consider a rigid object. This means it will not deform. For example, I have the racket, and we can imagine three different rotations. Imagine that we have an axis here, so we have this rotation. We have an axis here, so we have this one. And finally, we have an axis here, so we have this rotation. So the first two that I mentioned are stable, in the sense that nothing weird will happen when we are observing this rotation. But it's not the case for the last one. So what one will expect is that if I try to do a whole turn on this direction, if at the beginning of the movement I was watching the black face of the racket, at the end of the movement I will see the same black face of the racket. But this will not happen. What will happen is that at the end of the movement I will see the opposite face of the racket, and this means that there is an extra flip in the rotation. Now I will show you. I hope it will work. So I start with the red face of the racket, and then I will try to do a whole turn, okay? So after a whole turn, I see the black face of the racket. So this means that there is an extra flip, an unexpected one, and this is the tennis racket effect, this extra flip that we observe in this direction. So now, we want to work with ordinary differential equations. So in order to model the system, we are going to use the Euler angles, because they were introduced by Euler. And if we have the convention that for the tennis racket effect, for the tennis racket, I put the z-axis here, the x-axis here, and the y-axis here, then the two angles that interest us is the rotations around this one that will be codified by the angle phi, and the rotations around this one, and that one will be codified by the angle psi. Then Euler also gave the ordinary differential equations describing the movements, these rotations of rigid objects. And notice that we have this ordinary differential equation, and we have some parameters. We have the parameters Ix, Iy, and Iz. These parameters are positive parameters that are called the moments of inertia of the body. I will give you the formal definition of these parameters, but I want to give you the intuition. What is this telling us? So these parameters codify the shape of the body because they measure how the mass is distributed around a given axis. So for example, if I consider the y-axis here, then the mass is not very far away from this axis. But for example, when we are considering the x-axis, the mass is farther away from this given axis. So with this convention, we'll have, for example, this inequality, that the moment of inertia with respect to the axis z, it's smaller than the one in the axis x, okay? I will give you the definition after. But I want you to keep this, this intuition, because this is also telling us how asymmetric is the object that we are considering. So with this notation, the tennis racket effect, it's to have a variation of the angle psi. This means the final value minus the initial value, almost equal to pi along a trajectory. This means a solution of Euler's equation, such that the variation of the angle phi is equal to 2 pi. This is what we want to study. But now, I told you that we want to see if there are some difference when considering physical restrictions and when we don't consider these physical restrictions. So what are the physical restrictions for this problem? In order to explain you that, I need to give you the formal definition of the moments of inertia. So the moments of inertia of the body are given by integrals. I will explain you now these integrals. So basically, I will not draw the tennis racket, but I will have a potato here. And I will have the axis. So here I will put z, x, and y. And then for a given point on the body, so for example, this is the point R, we have that this has the coordinates x, y, and z. And there is a function that it's called the mass density, that it's telling you how the mass is distributed on the body, on the object. So it's like for every point, it's telling you how much mass you have on this point, okay? So this is the mass density. And then the integral that we are going to have there. So for example, for the axis x, it will be the integral over the body. So it's my potato here. And here I will have the mass density. And then the distance to the given axis that I'm considering here. So I put y squared plus z squared. And we do for every point of the body. So the moments of inertia has a property that says that every time that you take two of them and you add them up, the result will be bigger or equal to the third one. So basically, this property. And it's very easy to see why. So let's consider, for example, Iy plus Iz. So this, by the definition, just the integral of over the body. Here we have the mass distribution. Then here we'll have x squared plus z squared. And for the second one, we have, again, the same. And we'll have x squared plus y squared. Okay? So now, what we obtain here, 2x squared plus y squared plus z squared. And then, since this is positive, we have that this sum, this result, is bigger than this one, okay? So we have these three inequalities, but we remember that we had this assumption that we have the inequality, it's z, y, and x. And then it's very easy to see that since we have that assumption between these three inequalities that we obtain here, then there is just one that is not trivial. The other ones follow from this inequality that we have here. So the one that is not trivial, it's exactly the one that I put here. So it's the sum of these two, it's bigger or equal than Ix. And this is the physical restriction on this system. Okay, so I told you that what we want to do is to detect if in the geometry of the dynamical system we can detect some difference when considering this inequality or when we don't consider this inequality. So for this reason, what we did is to introduce a definition. It's when we are considering this inequality. So we called the physical case when we are respecting this inequality in the moments of inertia. But it's not very easy to work with this inequality. So there is an easier expression for this inequality that it will be more useful. In order to introduce this other expression, we introduce the asymmetry parameters. These two parameters, A and B, basically are codifying how different are the moments of inertia, A for Y and Z, and B for Y and X, okay? So I will write them here. And it's very easy to prove that this inequality that we have here now in terms of A and B, it's equivalent to have this inequality with the constants A and B. And this is the one that it's very useful to do the study. So we are going to introduce the geometric constant in the sense that it's not a dynamical information. It doesn't depend on time. It depends only on the shape of the object that we are studying. So in this case, we have that once that we introduce this geometrical constant, we have that the physical case is when this constant is bigger or equal to 1. So now this is the physical case. Okay. So again, I told you that we are going to see a difference in the tennis-racket effect. So what is the tennis-racket effect? It's to have a variation of the angle psi almost equal to pi along a trajectory such that the variation of the angle phi is equal to 2 pi. And notice that we don't care about the time. The only thing that we want to study is the variation of two angles, the angle phi and the angle psi. But we don't care about the time dependence. So what we're going to do is to consider the derivative of psi with respect to phi and the derivative of theta with respect to phi also. So we have this reduced system, which is exactly, it comes from Euler equation, just using the parameters A and B. So now we are in a very comfortable place. We have an ordinary differential equation with two variables. This is the things that we were studying in previous week. And moreover, it's even better, we have a first integral for this system. So for people who don't know, it's a first integral. In general, if you have an ordinary differential equation, so let's say that this is on R2, just because we are considering two variables here, then a first integral, it's a function that goes from R2 to R, such that the time derivative of f composed with a solution of the differential equation here, it's equal to 0. And this definition is telling you that the function f is constant along the trajectories of the vector field that you're considering. Or another way of saying that, the solutions to the differential equation are contained on the level curves of the function f. So for this equation, we have this first integral for the system, and then the only thing that we need to do to obtain the phase space of the is to consider the level curves of the function c. So of course, this c depends on the parameter a and b, but basically what you are going to obtain is this shape of the phase space. So I want to highlight the different objects that appeared last week. So last week we saw that the red trajectories like these ones are called periodic orbits. A fixed point of the differential equation like this one, it's a center point. The black trajectory that we have here, it's a separatrix, and then the fixed points that we have here are saddle points. So we have all these elements, and now what we are going to do is to simplify a little bit the problem. How we are going to simplify the problem? We are going to assume that we have symmetric initial and final conditions for psi. This means we are going to consider this initial condition, this final condition, along a trajectory such that the variation of phi is equal to 2 pi. Notice that in these ordinary differential equations that we are considering now, phi plays the role of the time now, okay? So to consider this, it's the same as considering this small part of the phase space that we just saw. So I'm going to put it here because I will use it later. Okay, so we have, it will not very scientific like there, but So here we have sine, we have theta, here we have pi, then we have the center point, we have two saddle points here, we have the separatrix, we have these open trajectories here, and the periodic trajectories inside. These 2 points are minus pi over 2 and pi over 2. So basically what we are doing is to consider trajectories that start near this point and then go near this other one in the time equal to 2 pi, because here the time it's the angle pi, okay? So what we can do, I will give an interpretation of the parameters c and epsilon. So basically, epsilon, it's the twist defect in the sense that if epsilon is equal to 0, then the variation of the angle psi is exactly equal to pi. So epsilon, it's measuring how far we are from this perfect twist. Then for c, it's the values of the first integral, but in fact, it's also easy to see that this c on the separatrix, it's equal to 0. Then for the trajectories that we have inside here, c is negative and start to be more negative when we approach this point. And outside, c is positive, and also it starts to be bigger when we are approaching these lines. So we can interpret the values of c as the distance to the separatrix. So we can consider for every value of c, we'll have a curve on this phase space, and we can associate to this value of c the corresponding twist effect. And what we have proved is that, in fact, the set of these values c and epsilon forms a curve given as the graph of a function epsilon of c. So now we are going to have in this space c epsilon, and we'll have a curve there that we are going to call c, the curve c, which is the curve of the tennis racket effect. And it's on this curve that we will see a difference when we are considering or when we are not considering the physical case, that is when we consider this inequality. So now we are ready for the first result. So the first result is that this function c associated to the tennis racket effect is an injective, and moreover it's a decreasing function, if and only if we are on the physical case. So we already see a difference on the geometry of the equation, and here I put some graphs. So for example, if we are on the physical case, we need to have I greater or equal to 1. So for example, here we have these two values, the value green and the blue one. So we can see that they are injective decreasing functions. But for example, for the value, for this value, even if it's quite close to 1, we already see that for this one, the function that we consider is not injective. And then the question is, can we say more for the behavior of the curves? Yes, so the non-injectivity, I will use it here. So basically, what we are doing here is to consider some parts of the trajectories that goes from near this point to this point, okay? So let's say, for example, from here to here in time equal to 2 pi. So what starts to happen in the non-injectivity case, which is the non-physical case, by the way, it's that at some point you start to need to use more than the whole trajectory. So for example, you need to go from here to do this, okay? And then these two values of epsilon, you already used them for another trajectory here, okay? So this is the interpretation of the non-injectivity for the non-physical case. So can we say more for the non-physical case, for the curves on the non-physical case? In order to do that, I need to introduce the curve S. Oops. That in fact, it's this red curve that I have here. So now I will introduce the definition of this red curve S. So I think I didn't put it. I will go back to this equation. So notice that in the first equation, we have the two angles that we want to study. We have the angle psi and the angle phi. And this is given by this formula. So in this formula, the only thing that bothers us is this term cos theta. Because imagine that we don't have this cos theta, then we can analyze the tennis racket effect from this equation, because we'll have the variation of the angle psi with respect to the angle phi. But in fact, we can solve this problem using the first integral of the equation, because from the expression of the first integral c, we can obtain this expression for cos square of theta. And then we can replace this on this equation. And the tricky point is that we need to be careful how to choose the sign that we will obtain here. So basically, if we do that, we'll obtain this equation instead of this one. And here, we need to be careful when we choose either the positive sign or the negative side. But this corresponds to choose when cos theta is positive or negative, and then to detect this change of sign, the only thing that we need to do is to see when this is equal to 0, to detect when we are changing sign. So for the initial conditions that we consider for psi, that it's minus pi over 2 plus epsilon, we'll have that this change of sign that corresponds this equal to 0, it's equivalent to have c equal to minus b sine square of epsilon. So this is the curve S that I showed you before. So basically, if we have this curve S, we'll have another curve here. The intersection of this curve S with the curve C of the tennis racket effect implies a change of sign in cos theta. So how to read all this information? So for example, put again this space here. So we have the value of the first integral, which is the distance to the separator, the twist effect epsilon, and then here we'll have a curve, which is the curve C given by the tennis racket effect. Here we have the curve S given by the equation that I showed you before. And basically, for example, to see that we can read some information from these graphs, if we have an intersection of the curve C with this axis, this means that epsilon is equal to 0. And epsilon was the twist defect. This means that we'll have a perfect tennis racket effect there. Then, if we have an intersection between C and this axis, this means that C is equal to 0. And C was the distance to the separatrix. So this means that here we'll have the tennis racket effect on the separatrix, considering this trajectory. And then, what I just told you, an intersection of the curve C of the tennis racket effect with the curve S that detects the change of sign of cos theta will give us this information. So now we can read this change of sign in terms of intersection between these two curves. So by doing that, we can say more about the non-physical case. So basically, for the non-physical case, we have that if the geometrical constant is smaller than this quantity here, then we'll have at least n plus 1 intersection points between these two curves. And this means at least n plus 1 times we're changing the sign of cos theta. And moreover, the curve C has an oscillatory behavior. What do I mean by oscillatory behavior? So basically, here again we have C, we have epsilon. Now we have the curve S, it's something like that. And what we see for the non-physical case is that we will start to have, for example, one intersection point here. So we have an intersection point. Then we are going to cross the vertical line epsilon equal to pi over 2. Then we are going to have another intersection point. We cross this line again, another intersection point, and like that. Okay? And this number of intersection points, it's given by this inequality. This means that if you consider the geometrical constant smaller and smaller, which means farther and farther away from the physical case, you start to have more and more intersection points on that graph. So the behavior starts to be more complex on that space. So I have some other graphs. So for example, it's very nice because now I didn't put the values of I for these curves, but we can easily see which curves correspond to the physical case and which ones correspond to the non-physical case. So for example, we have the blue trajectory, which is a decreasing injective function. So we know that this corresponds to the physical case. The same for the black one. But for the green one, we know that this already is a non-injective function, so we are in the non-physical case. And moreover, for example, for the pink trajectory, we have more intersection points with the curve S than with the green one. This means that the value of I for this pink trajectory, it will be smaller than the other. So we can read information from the geometry of these curves. And now I will just say a word about the proof. Like the key point of the proof for these properties was to consider for these trajectories the function that gives you the period with respect to phi here. So this will depend on the value of C. And to analyze the period here and the limiting behaviors. This means the infimum value and the supremum value that this period can have. And when doing that, analyzing these limiting behaviors, the geometrical constant I appears, and that's why we can prove these properties with respect to I. So I think that it's very nice that we can see a difference from the geometry of the differential equation, in this case for the tennis racket effect, when we are considering and when we are not considering the physical restrictions, because it's not very natural, or at least for me, it's not, to think you have a restriction that comes from nature or whatever, and you will see an explicit sign on the geometry of the dynamical system. And moreover, just like a fun fact, the non-physical case that we are considering here, even if we call it non-physical because it means that we are not respecting the physical constraints, this system, it's related to a system in quantum mechanics that it's used for quantum computing. And we know that quantum computing now, it's very trendy, and even the physics Nobel Prize, it was around quantum computing. So even the non-physical case has a physical interest. So these are the results. This is part of the results of this paper. And now in the time that I have left, I want to show you a previous result that we obtained about the tennis racket effect, just because it recovers this idea that was introduced by Ilyashenko last week, that sometimes you have a real problem, and if you complexify, you can obtain more information that it's useful also in the real setting. So that's why I will introduce the other results. Basically, here we said that we can replace this term cos theta with value, replacing with the first integral, okay? So we had something with a square root, an expression, and we can use this function that we obtained here once that we replace the expression of cos theta, and we can use this to analyze the tennis racket effect. How? We need to be in the part where cos theta is positive, so we are not going to move from this part. So we take the positive square root, and basically, to have the tennis racket effect, it's to have a solution epsilon from this implicit equation. So given a value of c, you have all these integral equal to 2 pi, and a solution for the tennis racket effect is to find epsilon such that it fulfills this equation, okay? So now, after a change of coordinates, we can change the expression of this integral, and we can obtain something like that. And notice that this is very nice because we replace an expression with cos square of psi with an algebraic expression for the integral. So here we have just that alpha is equal to that and beta is equal to that. So what we have done is to define the function, which is to take this integral, and instead of putting that, we are going to put a variable here. But it's exactly the same function. This function depends on A, B, this means the shape of the body, and C, which is the distance to the separatrix. With this notation, we'll have just that the variation of the angle phi is equal to this. And here, notice that we have a real function, but we can complexify it. It's the same as the idea as before. So now we consider on this function x to be a complex number and u to be a complex number. If we do so, the natural place to study this function is on the Riemann surface. Maybe here it's P, given by, I will take exactly the same polynomial there. Given by this equation. Here it's just x. So, the natural place to study this function, it's in the Riemann surface given by this polynomial. It's exactly the same one that we have here. And then we have y squared, okay? Because y is equal to what we have here. What we have done is to study this function on this Riemann surface and find that it has different behaviors on this function. And this information allowed us to prove this theorem in the real setting that says that for sufficiently asymmetric bodies, this means B different from 0 and A sufficiently big, we'll have an initial condition close enough to the separatrix such that we observe the tennis racket effect with twist effect epsilon small. And in fact, we can see that this is true. This theorem is telling you that you need to have enough asymmetry in your body in order to observe the tennis racket effect. So you already saw that for the tennis racket, it's true. But now I have this that it's almost the same. It's also an asymmetric body because I put this small thing here. But this is not very asymmetric compared with this one. And you will see that we cannot see the tennis racket effect on this one. So I put a sticker on this side to identify both sides of the object. And then when I try to do a whole turn here, what I obtain always, it's exactly the same phase that I see at the beginning. Okay? I don't see the tennis racket effect. So this theorem is telling you that you need an asymmetric enough rigid body in order to observe the tennis racket effect. This is one of the results on this paper, and that's all. Thank you very much.
Are there any questions or comments?
So I want to ask when you put the different curves, I think that are the C curves in that, yeah. The difference between, because the blue and the black one are both the physical case.
Yes.
But in one, so the convexity changed. So what is?
Yes, this we haven't studied. We haven't seen if there is a difference on the convexity or not. But it's true that we can see that there is this difference. It will be interesting to see if we can say something about it. Like maybe if you are closer to 1, then at some point it changes the convexity. Because what happens here is that this black trajectory, it's for a value of I closer to 1, okay? Because that's the limit case when we start to be a non-injective. So maybe at some point when changing the value of I, the convexity change, but we haven't studied that.
Okay, thank you.
Thank you.
Another?
Has Poinceau something to say about this?
About what exactly?
This problem.
In which sense? I mean, what I told you before is that, for example, these curves, maybe, I don't know if it was clear, but with these curves, we are changing every time the parameters A and B. This means that we are changing the shape of the body. But at some point, we go out from the physical possibilities and we start to have these curves. But for example, all these behaviors are the different curves that describe how these parts of the trajectories that we are trying to study behave. So we start to change the parameters A and B, we start to change the shape of the body, and then these parts of the trajectories that we need start to change. How they are changing these curves are telling you how epsilon is changing with respect to the initial condition, let's say. So this is the information that we can recover here. So the tennis racket effect is to consider these parts of the trajectories, and these curves are describing how this is changing when we are changing the shape of the body. Yes. Yes.
And the initial condition shows that the pendulum goes right.
Yes.
But why different? Can you explain the difference in this case with your computation?
Yeah, in this case, it's also the same thing. Like, we cannot be exactly on the separatrix. This will not correspond to a position or a rotation in the body. It's the same thing. And then, but for the rest of the trajectories, they are physical, like possibly. You can have trajectories on these other ones. But this is a different physical and not physical. Because here, the things that we are calling physical and not physical just depend on the parameters that we are considering. Because we have these restrictions on the moments of inertia, and this is what we call non-physical. But for a given parameter such that we have a physical rigid body, it's true that you cannot be exactly on the separatrix. This it's the same in this case. But it's a different study.
Thank you. Just one question. Can you say a word about the monster flip?
In which case? So for the monster flip, what is the monster flip? Yes, yes. So what is the monster flip? What we have seen is that for the tennis racket, it will almost always happen that we have an asymmetric body, so the tennis racket, and we saw that every time that we want to perform a whole turn in this direction, we see the opposite face of the racket. So now imagine that this is not a racket, this is a skateboard. So this is the skateboard and we are skating. This means that we have the wheels here, and imagine that you want to do a trick such that you want to perform a whole turn of your skateboard, but you will have a problem if you see the tennis racket effect. Because if you have your wheels here, the tennis racket effect says that at the end of the movement, the wheels will be facing you, and you don't want that. But some people in the US started to try to do this effect, and they could do it. So we did also some study in this paper to analyze the initial conditions that you need, which are very, very specific and very, it's almost impossible to be exactly in these initial conditions, but there exist some initial conditions such that even in an asymmetric rigid body, you will avoid the tennis racket effect. And this explains why they could do this skate trip, which is called the monster flip.
Okay, and another question? Okay, if not, we thanks Gabi.